Hello everyone and welcome back to Techmine Guru. If you have ever felt your code slowing down when hunting for a simple value, today is the day we change that forever. I am Supratim, your coach, and today we are unlocking one of the most powerful optimization in programming. We are officially diving into DSA lecture 26 to master binary search on arrays. Today is all about the art of halving your search space. Before we jump into the code, let's look at where we stand in our code structure. In phase 1, forging your toolkit, we started with module 1, covering foundations and array patterns. This includes our intro to problem solving, time complexity, and big O notation, arrays and memory, prefix sum pattern, carry forward and subarrays, sliding window technique, basic sorting, 2D matrices and strings, and bit manipulation basics. And in last module 2, we learned about advanced arrays, recursion, and number theory, where we learned about advanced array optimization, advanced 2D matrix problem, advanced bit manipulation, how to think recursively, modular arithmetic and GCD, introduction to hashing, and finally, we learned about two sorting algorithms, which are merge sort and quick sort, and along with some comparator problems. Now we have officially entered phase 2, where we will master the landscape. So in this, we are currently in module 3. So we are going to start module 3, the code structures. Today, we are going to see the binary search. After this, we will see binary search on arrays, what are linked list, and how to do traversal, reversal, and find cycles in a linked list, what are stacks and queues, and some problems on stacks and queues. Then we will introduce tree traversal, and finally, we will go to binary search tree. After that, in the next module, we are going to learn about some advanced techniques like combinatorics and prime number problems, two-pointer techniques, backtracking of subsets and permutations, advanced linked list, LRU cache implementation, advanced trees like lowest common ancestors and views problem, advanced hashing, and finally, we will move to the module 5, which will be our expert level, where we will learn about heaps and priority queues, greedy algorithms, dynamic programming, including 1D and 2D DP, knapsack DPs, graphs, DFS, BFS, and some graph algorithms like Dijkstra's. And finally, we will complete the course by introducing to topological sort and minimum spanning tree. So let's look at our specific agenda for today. So today, first, we will do an intro to searching, comparing brute force versus binary search. Next, we will learn about standard binary search using some dry run. Third, we will tackle the mid overflow trap and learn the safe formula. Fourth, we will figure out finding first and last occurrence. Fifth, we will hunt some local minima. And finally, we will solve for finding square root problems. To succeed today, you need to understand three core terms. What is search space? What is a target, and what are the conditions? So the search space means the specific area where we know the result can exist, and going forward, we will search only in that search space only. And for the target is the exact item or element we are looking for. And what is the condition? The condition will be the logic which used to discard a part of the search space, shrinking it until we reach the desired result. So let's start with a classic problem, finding a target K in a sorted array. So if you apply brute force, that is if you run a loop from I to length of the array, then you have to iterate the complete array to get a desired result. So since you are running one for loop, so the time complexity will be O of n. Linear search is like a brute force approach. But with binary search, we will drop that to time complexity of O of log n. So let's see how we can do that. So for doing that, we have three essential steps which we need to follow. So the first step would be to define your search space, which is between 0 to n-1. Then the second step is to check if middle element is our answer or not, which we can get by using this formula, mid is equal to L plus R by 2. And third, we have to decide whether we need to go left or right to get our answer. So to define your search space from 0 to n-1, in code, we write L is equal to 0 and R is equal to n-1. And we run a loop from L to R. So this is our first step. Next, for the second step, we will check if the middle element is our answer by calculating mid is equal to L plus R by 2. And in that, if A of mid is equal to K, we will return mid index as the result. So this is our second step. And finally, in our third step, we have to decide whether we need to go left or right. So if K is greater than A of mid, in that case, we will go right, where we will do L is equal to mid plus 1. And if K is lesser than A of mid, in that case, we will go left. And for going left, we have to do R is equal to mid minus 1. So you can understand that with this diagram. Suppose your mid element is here, but you want to search an element somewhere here. So at that time, in first iteration, we will get mid here, right? But in the next iteration, we can get answer here only because K is lesser than A of mid, right? So we will discard this search space and we will start watching this search space. So for that, we are moving towards the left. And when we are moving towards the left, we will make our right pointer as mid minus 1, right? So let's see the code for that. The code is very simple. We have just applied the above three steps here in the code. We have taken two pointers, L is equal to 0 and R is equal to n-1. We ran a loop from L to R. We calculated the mid element, which is equal to L plus R by 2. We checked whether that element present in the mid is equal to K or not. We will return mid from here. If K is greater than A of mid, that means we will get result somewhere in the right search space. So we will bring our L pointer from L is equal to 0 to mid plus 1, right? Similarly, if k is lesser than a of mid, then our search space will be this much only, and we will bring our right pointer to the left side by making r from n minus 1 to mid minus 1, right? So let's understand that with a dry run. So suppose the example given is a is equal to 3, 6, 9, 12, 14, 19, 20, 25, and 27. And we are searching for k is equal to 12, right? So initially we will define L and R. So L will be at 0 and R will be at 9. Since the range of the array is 10, so the R will be 9 only. Now the mid will be equal to L plus R by 2. So what will be 0 plus 9 by 2? It will be 4. What is the element present at the fourth index? 14, right? Now we will check whether k, which is 12, is lesser than a of 4 or not. If it is lesser than a of 4, that means we cannot find that anywhere in the right search space, right? So we will move left, and for moving left, we will do R is equal to mid minus 1. So L will not change here. So L will be again 0 and R will be now 4 minus 1, which will be equal to 3. Now we will again calculate the mid, right? So that will be 0 plus 3 by 2, which will come as 1. So what is the first element? 6. Now our search space is reduced from here to here only. Now since we got 6 as the next mid, we will see whether 12 is greater than the mid element or not. We will see 12 is greater than mid element. So we will bring the L pointer towards the right side. So for that, we will do L is equal to mid plus 1. Now our search space will reduce from this one. Since the mid is 1, in our next iteration, the L will be equal to 2 and R will not change. So now our mid will be 2 plus 3 by 2, which will come 2. So what is the second element? 9, right? We will again check whether 12 is greater than a of 2 or not, which is 9. We will see 12 is greater than 9. So we will again move towards the right. So our L pointer will now come here. So our L will be equal to mid plus 1. Now what was our previous mid? 2. So L will be equal to 3 and R will be equal to 3. Now our current mid will be 3. And since we reach the current mid, this condition will tell that we have found the element and it will return the result. So if you see that on every iteration, our search space is becoming half. First, it was like this much big, then it was like this much big, then it was like this much big. Like this, our search space will keep on decreasing on every iteration. So our iterations will be n to n by 2, then to n by 4, and then finally we will reach that element where our iteration will be 1 only. So if you remember from our previous classes, our time complexity will be log on the base 2n. So let's level up to level 2, where we can apply this binary search. So the question says we have to find the first occurrence of that particular kth element in our array. So we have been given an example a, which is equal to -5, -5, 3, 0, 0, 0, 2, 5, 7, 7. So since k is equal to 0, so our desired result will be this 3. But since we have to find the first occurrence of that target element, we will just focus on the first occurrence. So in this, we need a slight logic shift. So we will initialize L is equal to 0 and R is equal to n minus 1. We will keep an answer variable saying that we have not got the index. We will keep it at -1. We will run a loop from L to R. We will calculate mid using the formula L plus R by 2. Now we will check if A of mid is equal to k or not, that we have reached the target element or not. Because if we get this 0 as well as the first mid, then also this A of mid will be equal to k. But we are not sure that whether we got the first occurrence or not. That's why we will save the mid index into the answer. And since we have to calculate the first occurrence, so for calculating the first occurrence, we have to intuitively move towards the left side of the array. So for that, we used R is equal to mid minus 1. Now, the remaining two conditions will be similar. If A of mid is greater than the target element, then we will move towards the left side. For that, we will do R is equal to mid minus 1. And if A of mid is lesser than the target element, that means we have to move towards the right side. For that, we will do L is equal to mid plus 1. So let's see the dry run for the same. So initially L is equal to 0, R will be equal to n minus 1. So R will be 9, right? Answer will be -1. We will run a loop from L is lesser than equal to R. Because as soon as any of the pointers will cross each other, we have to break out from the loop. Now we will calculate mid element. So our mid element will be 4, right? And what will be A of mid? A of 4 will be this 0, right? So we will keep in the answer as 4 only. And since we know that we have got the element and we don't know yet we have got the first occurrence or not, we will simply move our R pointer to the left side by making it R is equal to mid minus 1. So now R will be equal to 3. Now again, this while loop will check 0 is lesser than equal to 3. Now it will calculate the mid element. The mid element will be given as 2, right? So what is the second element? It will be -3. So we will check if A of mid is greater than k or not. So this condition will not work. So this condition will work. Since our mid is 2, our L will be 3, right? Now again, in the iteration, we will check if A of mid is equal to k or not. We will say yes, A of mid is equal to k. We will again store the answer as 3 and we will again move to the right side to make sure that this is the first occurrence. So now R will be equal to 2. But if you see, now our final R is 2 and our L is 3. So this will violate our while loop. Code will break from here and it will return the answer. What is the current value of the answer? It will be 3. So this is how we got the first occurrence. Similarly, you can find out the last occurrence as well by just tweaking these two condition and here by changing it to L is equal to mid plus 1. So this is a lead code problem. The link I have mentioned in the description as well. And since you can see that every time our search space is reducing to half, so our time complexity will be O of log n. And since we are not taking any extra space, our space complexity will be O of 1 only. Now let's level up again. Let's find the local minima in our array. So suppose you have been given an array and you have to find the elements which are becoming local minima. What is the definition of the local minima? That every a of I must be smaller than both of its neighbors. That is, a of I minus 1 should also be greater than a of I and a of I plus 1 should also be greater than a of I. So for this, if you see 3, there is no left, right? But in right, it is smaller. It is smaller than 6. So 3 is one of our local minima. Similarly, when we reach to 1, we will see left element, which is 6, which is greater than 1, and right element is smaller. So this is not local minima. Similarly, if we see 0, the left and right, both the elements are greater than that. That's why 0 is our local minima. Similarly, if you see for this example as well, here 1, 3, and this 8 will be considered as a local minima. So let's understand the local minima with 4 cases. So suppose case 1 is where the local minima is becoming like a valley, where mid minus 1 and mid plus 1 are both greater than the mid. Similarly, we can get local minima if mid element is greater than mid minus 1. That is downwards left. Similarly, if mid plus 1 is lesser than mid plus 1 will be somewhere here, right? And mid is greater. So if it is downward right, then also we will get a local minima. Similarly, if both mid minus 1 and mid plus 1 are lesser than mid, then also we can get a local minima. At that time, we can go any of the side. So for case 1, when mid was lesser than mid minus 1 and mid plus 1, we have to return mid from there. And when we have downward left, that is mid is greater than mid minus 1, at that time, we only have to move towards left. Similarly, when we have downward right, then in that case, we just have to move towards the right side. Similarly, if we have got the peak element where mid is greater than mid plus 1 and mid minus 1, we can go either of the side and we can get the local minima there. So let's see the code for the same. So again, the code is similar where L is equal to 0 and R will be equal to n minus 1. We ran a loop from L to R. Here we have calculated the mid formula using this formula, which is again equal to L plus R by 2. So we will learn why this formula is preferred over this one in a short while. So here, for checking the boundary condition, we will do that if mid is equal to 0 and a of mid is lesser than a of mid minus 1, either of this formula, or mid is equal to n minus 1 and a of mid is lesser than a of mid plus 1. So either this condition should work with this condition, because when mid is equal to 0, mid cannot be equal to n minus 1, right? Or else this condition should work with this condition. So this will prevent our index out of bound issue. And whenever we find a of mid, which is lesser than a of mid minus 1 and a of mid plus 1, we will return a of mid as the answer. And in case where our mid minus 1 is greater than a of mid, that means we have to go right, because it is our case 3, where a of mid is greater than a of mid plus 1. So for going right, we know we have to do L is equal to mid plus 1. And similarly, if a of mid minus 1 is lesser than a of mid, which is case number 2, at that time we have to go towards the left side. And for going towards the left side, we use R is equal to mid minus 1. So again, if you see, our search space will get reduced. So any of these 3 answer will give the result. So let's see that with this dry run. So our L will be 0 and R will be 7. What will be mid? 4, right? We will check if 4th element a of 4 is lesser than a of 3 or not, and we will check whether a of 4 is lesser than a of mid plus 1, which is 9. Since this condition will satisfy, so we will return saying that this is the local minima. Since every time the search space will reduce to half, so our time complexity will be O of log n. And since we are not taking any extra space, our space complexity will be O of 1 only. So let's understand why we wrote L plus R by 2 as L plus R minus L by 2. So we have to address this as a best practice so that we don't get trapped into the overflow issue. Assume you have int max is equal to 100 for a system and you have L is equal to 80 and R is equal to 90. So when you calculate L plus R by 2, it will give 170 by 2. So since this 170 will be out of int max range, so the program will get crashed before it can divide by 2. So we will derive this formula using this formula. Let's see how. So L plus R by 2 can be written as L by 2 plus R by 2, right? So if we write like this, Suppose for given example 5, where L is equal to 5 and R is also equal to 5. So what should be our mid? L plus R by 2 should be equal to 5. But if we just break this formula into these two halves, we will get 5 by 2 as 2, 5 by 2 as 2, and 4 as the answer, which is wrong. So what we can do for this, for getting this, we will simply add and subtract L from both the ends. So if you closely look this, L by 2 minus L, what it will be? Minus L by 2, right? So we have taken this R by 2 minus L by 2 in one place, which made it R minus L by 2. And since we have not touched this L, so this L will remain as it is. Again, if you open this formula, you will get L plus R by 2 minus L by 2 only. Again, this minus L by 2 will make this L as L by 2 only. So we will again reach from this formula to this formula again. But using this approach, we will be safe from our overflow trap. How? Let's see the same example. So now L will be equal to 80, right? R will be equal to 90. So here 90 minus 80 by 2 will give result as 5, right? And we have 80, then the final result will be 85, which is our desired result. And also because of this minus, we just escaped the overflow trap. So let's see the last problem of our day today, which is to calculate the square of a given number. Suppose example is n is equal to 50. So we will not bother about the decimal points. So here the biggest insight here is the search space isn't an array. The new search space is in the range from 1 to n. Since we already know that if we have to do the square root of any number n, it will lie between the range from 1 to n only, right? Root n will lie between the range from 1 to n only. So here, instead of checking a of mid, we will check mid into mid. And if mid into mid is lesser than the answer, we will consider this as answer and we will move towards the right. And for moving towards the right, we will do L is equal to mid plus 1. And if mid into mid is greater than n, we will move towards the left. And for moving towards the left, we will do R is equal to mid minus 1. So let's understand the same with the dry run. So for getting the square root from 1 to 50, so what will be our search space? So L will be equal to 1 and R will be equal to 50. So what will be our mid? So mid will be 25. Now we will check this condition. Since 25 into 25 will be equal to 625, which is much higher than 50, we will move towards the left side. So for moving towards the left side, what we will do? We will do R is equal to mid minus 1. So what is mid? 25. And what will be our new R? 24. Now L is 1 and R is 24. Now our search space reduced from 1 to 50 to 1 to 24. Now again we will calculate the mid. 1 plus 24 by 2, it will become 12. 12 into 12, which is again greater than 50. That means we again have to move towards the left side. And for moving towards the left side, we will do R is equal to mid minus 1. So mid is 12. So R will be equal to 11 now. So our search space will now become till here. So what will be our current mid? 1 plus 11 by 2 will be equal to 6, right? Now we will do 6 into 6, which is lesser than 50. Since it is lesser than 50, we have kept answer is equal to 6 and we have moved towards the right. And for moving towards the right, we will do L is equal to mid plus 1. So what is mid? 6. So our L will be 7. Now our L will somewhere come around here. Again, this search space will get discarded. So what will be our new mid? It will be 7 plus 11 by 2, which will be 9. Again, we will check mid into mid, which is 9 into 9, which is greater than 50. Since it is greater than 50, we will again move towards the left side. So our R will become mid minus 1. So our R is 8 now. Now, what will be our new mid? It will be 7 plus 8 by 2, which will be 7. Since 7 into 7 is lesser than 50, which means we can update our answer from 6 to 7 here. And we will move towards the right by making L is equal to mid plus 1. Now, since our previous mid was 7, so our L will become 8. Now, what will be our new mid? 8 plus 8 by 2, which is again 8. Since we know that 8 into 8 is greater than 50. So we will again move towards the left. Again, R will become mid minus 1, which is now will become 7. And since now L is greater than equal to R, this condition will break. So we will come out of the loop. And what will be present in our answer variable? It will be 7. And also we know that the square root of 50 somewhere around 7 point something. So the integer value is 7. So we have finally reached the goal. Since in this also we are applying binary search only, so our time complexity will be O of n. And since we are not taking any extra space, our space complexity will be O of 1. So let's summarize our breakthroughs today. The power. You just learned how to drop O n operations down to binary O of log n speeds, right? Also the mindset in which you have defined your search space, you have checked your mid element, you have discarded the half of the search space after getting the mid element. And finally, the pro tip is always use mid is equal to L plus R minus L by 2 so that we don't get overflow issue. So in our next session, we are moving on to lecture 27, where we will conquer binary search on answers. If you found this video helpful, hit that like button and subscribe to Techmine Guru. Till we meet again, keep learning, keep coding, and keep optimizing.